Hey guys, so we're ready to go over our notes for topic number 2. So please just follow along with the instructions that will appear on the screen here in the Edpuzzle video. Type in your answers to the questions as we go along, and hopefully we can get through this one a little bit faster than the last one. So first of all we're going to do a quick warm up, and then I'm going to walk through these notes. And since I don't have live demonstrations with you all, I do have some demonstration videos that we will go through together. And then at the very end, you're going to practice identifying types of reactions. So our learning target for this particular set of notes is to be able to identify the types of chemical reactions based on their equation. So now I'm going to take a minute and ask for you to, here, move my face out of the way, answer these questions in the Edpuzzle video, and please make sure that on your notebook paper that has your name on the top, that you write down the date for today, and then you write warm up, and you're going to write down all 5 of the answers for this warm up. And then, so not only will you write them into your notes, but you'll also type them into the Edpuzzle. And then we will meet back here in just a second. All right, so our first question was, what is or are the reactants of this equation? And so yesterday, as I explained to you all in our notes for topic number 1, the reactants are always going to be the things that are on, I think I'm going to go ahead and snip the screen and make it easier for me to write on and erase. Oh, look at that. That's from the other day. All right, so the reactants are going to be the things that appear on the left side of this reaction, because those are the things that are doing the reacting. So you should have told me both this one and this one, and you need to make sure that you write those down as is. You don't have to write the 2 for the H2O, but BaCl2 and H2O are both reactants for this particular reaction. The next question, does the equation above have a catalyst? You should have said no for this one. And the reason that you should have said no is because there's nothing that appears over the arrow. If there were a catalyst in this reaction, then it would appear right here over top of the arrow. And since there's nothing there, then your answer should have been no. Number 3 asks, in what state of matter do the reactants exist? So states of matter were, going to be these things that are in the parentheses after each of the compound formulas. Since we started and we're looking specifically at the reactants, so we're again back to that left-hand side, you should have said that they are aqueous and liquid. Now it's important to note that liquid and aqueous are not the same thing. Aqueous means that you've taken something and dissolved it into water, which is not the same as a liquid. A liquid is a pure substance that has either been melted and turned into a liquid, or sometimes you condense it from a gas and turn it into a liquid. So it's a state of matter based on how much heat is associated with the system. An aqueous solution is just something that has been dissolved in water. So it's not the same thing. So you should have said both aqueous and liquid. In number 3, it asks, what is the state of matter for the products? And since both of the products are aqueous, you should have said aqueous, and that's it. You didn't have to say anything else about that. Number 5, turn the following word equation into skeleton equation. So the first thing that you're going to do is try to figure out what the reactants are and what the products are in this equation. So we know that zinc nitrate reacts with, so zinc nitrate, you can't see it here because of this daggone color thing that was in front of it. Zinc nitrate is going to be one of the reactants, and sodium chloride is going to be the other, because they react together and they're producing zinc chloride as a product and sodium nitrate as the other. So let's figure that out. Zinc nitrate is an ionic compound. Let me get rid of that one. And I know it's ionic because zinc on the periodic table is a metal. It's going to be right here. And nitrate is a polyatomic ion, and its formula is NO3. So since this is an ionic compound, I'm going to have to crisscross the charges. NO3's charge is a -1, and if you look back here at zinc, it's a +2. So I need to take those formulas, down here, and let me erase this to make it easier to see. And since zinc was Zn, that's fine. And it has a 2+ charge, and nitrate is NO3, and it has a 1- charge. I'm going to crisscross those to get ZnNO3 too. and that is going to react with sodium chloride, and which is also going to be an ionic compound. And I know that because sodium is a metal and chlorine is a nonmetal. So sodium's charge is a +1 and chlorine's charge is a -1. So when I put that into a formula, again, it's going to be Na, which is a +1, and Cl, which is a -1. So that makes it neutral. And now I can make my products. Zinc chloride. So since I know that this is ionic because zinc is a metal, and again, this one will be 2, sodium is also a metal, I'm going to take my zinc, which is a 2+ charge, and my chlorine, which is a -1, and those will crisscross. So the Zn2+ is going to go down to be the subscript on the chlorine, and then I don't put ones as subscripts. My other product is going to be sodium nitrate. Sodium is a +1 and nitrate is a -1, so that one is neutral. So it will be NaNO3. So this whole thing should be your answer for number 5. All right, so let's go ahead and move on. All right, so we're going to start with our notes. And just like yesterday, if you have, access to a printer, you're going to go into the cloud calendar and you're going to print out this handout. This is your follow along handout for the notes. And after you print it out, then you can fill everything in. Or if you don't have access to a printer, you'll copy everything from this slide as far as the words go. You know, obviously don't have to draw pictures or anything like that, but you're going to write down all of the words from this slide. So go ahead now and fill in the missing information. All right, so 5 types of chemical reactions. So if I'm looking at an equation like this one, then I know that I can predict some things about it based on what its reactants are and what its products are and things like that. And there are 5 types of reactions that we're going to talk about so that we can kind of make some predictions about what the products would be if I only saw the reactants. The first of those being a synthesis reaction. Sometimes the synthesis reaction is also called a combination reaction, and the reason for that is because things will be combining to form one product. Notice that it says there are 2 or more reactants. So you'll have any number of reactants on the left-hand side. It could be 2, it could be 3, it could be 4. But one thing that has to be true all the time is there's only a single product. And so we can't have any plus signs on the product side. You should only have some in the reactants. So the first thing, gosh, I don't know how I end up doing this every time, but I can't even go backwards. Growl. Let's see, back. There we go. The first thing that I need to look at is whether I have more than one reactant or if I only have one product to determine if it's going to be synthesis. So I usually talk about how this is right around this time of year. We're going to prom and you have boy meets girl and they end up becoming prom dates and they started single and now they're one. So they should only have one compound on the right-hand side, which is the product side. This example right here is going to be the reaction that you all will be writing down because that's going to be the demo that is in the video that follows after this. You're starting with some powdered, I did it again, powdered zinc, and you're going to add or allow it to react with some solid iodine crystals. Once you take the zinc and the iodine together, the reaction of them combining into one compound is actually so slow that you wouldn't ever notice it. So to increase the speed, we add a catalyst. That's why that hydrogen, that H2O is over the arrow because we know catalysts appear over the arrow. So zinc is going to react with iodine. We add a catalyst to make it happen very quickly, and we are going to form zinc iodide as our product. All right, so I'm going to, this is kind of what a synthesis reaction also looks like in cartoon land. You have a fish, I'm sorry, that's a cat, and that's a fish. And when you have the cat and the fish separately, they're 2 separate beings, but then the cat eats the fish and now they are one, they are together, and we have AB. That's a synthesis / combination reaction. So we're going to watch this demo. I will press play. You're going to write down your evidence of chemical change on your notes. Let's see if I can find those really quickly. I think I might be able to. On the notes handout for today, here it is. You're going to write your observations here over to the side. Tell me, what is it that you notice that is evidence of chemical change as we go through it? I did it again. I swear I cannot touch this daggone mouse. I cannot control it. I don't know why it jumps around, but let's go ahead and wait on that again. So notice when they pour this in what the iodine crystals actually look like. You've got this black, almost brown. If you were to be able to look close enough, you'd probably see some sparkles that are in it too. And here comes our powdered zinc, which is also a very dull gray solid. We're going to allow them to come into contact with each other because reactions cannot occur unless there is contact. And now we're going to add some water. Sorry if you can hear my kids playing games in the background. And there is evidence of chemical change. So go ahead and write down on your notes paper what evidence you see. All right, so there you go. Evidence of chemical reaction. Okay, next up. So a decomposition reaction, go ahead and take a second here, fill in your missing information on your paper, and then we will go ahead and move on after that. Decomposition is the opposite of synthesis. So in a synthesis, we're actually putting things together to form one, but in a decomposition, it's just like it sounds. Things are breaking apart. They're breaking down and decomposing. So we have to start with only one reactant, and we're going to have more than one product. It could be two, it could be three, it could be more than that. The important part is you can only have one thing on the reactant side, but you're going to have multiple things on the product side, multiple compounds or elements. So for us, if I go back to the prom date scenario, you also could have the same situation where, after prom, things didn't work out. They break up. So now instead of the couple that we had at prom, now we go our separate ways and we're single again. H2O2 is hydrogen peroxide. So in this demonstration, which you're going to write this down here, if you haven't already on your paper, you're going to see some hydrogen peroxide that is going to decompose into water and oxygen gas. We're going to use a catalyst for it. I actually don't know in the video if they use Ki or if they use NaI, but they both do the same thing. So there's a catalyst because it is over the arrow. This is potassium iodide. And we're going to watch for evidence of chemical change. And then we are going to write that on our paper. So I also wanted to point out here in the cartoon chemistry. So here is where we start with things that are together as one, but in the product side, things are separated. So if I start with AB, then A is going to separate from B in the product. You probably have seen or heard of this before. This is going to be the elephant toothpaste demo, which is the decomposition of hydrogen peroxide. We use 30% hydrogen peroxide because of how concentrated it is. It will make things happen much more quickly and make the reaction easier to observe the changes. If you use just regular hydrogen peroxide that is in your house, it's probably 3%, so it's 10 times weaker. And it might give you a reaction. It probably won't give you as much or as quickly. So they added some soap. And the reason for that is because this happens so quickly or so slowly that we want to try to capture the gas, the oxygen gas that's being released, and we do that in soap bubbles. So here's a little potassium iodide they're preparing. I don't know that I really care about preparing the potassium iodide solution, so I'm going to fast forward past that. Why do we have to know about that part? All right. So now we've got some potassium iodide. We are going to add that to our hydrogen peroxide and watch for evidence of chemical change. And here it comes. So think about your 5 pieces of evidence of chemical change and go ahead and write your observations down on your paper. And I think they're probably just going to allow this to keep going. And again, because it's a catalyst, it doesn't get used up. It was just used to make it go faster. All right, next. Already did that. So now we're looking at a single replacement. Sorry, there goes the dog. Single replacement reaction. Go ahead and pause here and fill in the missing information. I'm recording, so just shh. Okay. So single replacement reactions are also called single displacement reactions. And this would be the scenario. Let's go back to prom. So we have boy and girl who go to prom together, right? Here's the happy couple prom, except that there is this other person who grabs the attention of, if this is, let's pretend this is boy, this is girl, there's another girl here. And I say this because a negative in an ionic compound can only be replaced by another negative. So if I have a metal and a nonmetal, another nonmetal comes along and kicks this one out and takes over and becomes the new dance partner out on the dance floor. Or another option would be if you have boy and girl and you have another boy that's out there, then the boy's going to replace the boy that's in the compound, kick them out, and take over as the dance partner. So now you have the girl who is dancing with a new boy. So it really depends on what the element is that's alone, on what is going to be doing the replacing and where it goes in the compound. I also want to point out that when C took the place of A, it literally took the place of A. It has to come first because the metal or the positive ion always comes first. So in the scenario that you're going to see, we've got copper chloride. So copper is the metal and chlorine is the nonmetal. And then aluminum comes along, and aluminum is a metal. So it can only replace another metal. So it kicks the copper out and takes the chlorine from it to become AlCl3. And then you've got Cu all by itself. Here's what's important. We have to have a pair with a single element on each side of the equation. So it can't be a replacement reaction unless there's a plus sign on both sides. And you're going to have a single element on both sides. It'll just be a different one. So you'll have compound element, compound element. Now, B could actually be before AC. It could be AB plus C yields B plus AC. That part doesn't matter, which part of the plus sign they're on. It just matters where they take the place in the compound. So a metal only replaces another metal, and a nonmetal will only replace another nonmetal. So in cartoon land, we started with AB, which is the dog with the bone, and then we have a steak. Well, steak is more attractive to the dog, so that poor bone gets kicked out, and the dog has got a new dance partner and leaves the bone standing at the table all by itself while it dances with the steak. So since C took the place of B, B came first, which is fine, and then it becomes AC in the compound. All right, so let's see what happens here. So tiny piece of aluminum in a test tube, and we're going to add some copper chloride to it, copper 2 chloride. Start taking notice of any changes that you might see, evidence of chemical change, and then make sure you write that down on your notes paper. So they just did like almost a fast forward. So what you should be noticing is that what was aluminum, that silvery, shiny metal, has now turned into this copper color. And the reason is because the copper that was in the copper chloride solution has now come out of the solution to form, those are just copper atoms now that look copper. And the aluminum that was on the foil has now gone into solution to become aluminum chloride. So it's a single replacement reaction. Aluminum took the place of the copper in the solution, and the copper came out of the solution. All right. Next one is a double replacement reaction, or also known as a double displacement reaction. So in this one, you've got two pairs of things. I usually refer for this scenario to when I was in college. I had a roommate I didn't get along with. And then my friend down the hall had a roommate she didn't get along with, but our roommates got along. And so we just did a switcheroo. So our roommates just traded rooms, and she moved in with me. And then my roommate moved in with her roommate. So we have partners that are just going to exchange. It's sort of like a square dance when they say, do-si-do and change partners, whatever it is you did in elementary school. We start with two ionic compounds. We have a metal and a nonmetal, another metal and a nonmetal. And what happens is the two nonmetals will trade places, or I guess you could say the two metals, it doesn't matter, but they exchange partners. So the first metal bonds with the second nonmetal, and the second metal bonds with the first nonmetal. It is important to note, because this is something that gets missed a lot, that in our new compound, those should be over a little bit, it should be plus then minus, then plus then minus. And that is why the C had to come first here and the A had to come first there. All right, so down here, the reaction you're going to see is sodium iodide with lead 2 nitrate. We're going to allow these two ionic compounds, which are in solution, they're aqueous, to mix together. And then we're going to see what the products of our compounds will be. So this is just another scenario with cartoons. We've got the bunny with the steak and the dog with the carrot. Bunnies generally like carrots better than steak, and dogs generally like steak better than carrots. So they're going to exchange partners, and the bunny will pick up the carrot and the dog will pick up the steak. So we've got AB and CD and then AD. All right, so they're just going to exchange partners. So let's see what the demonstration looks like for this. So that's potassium iodide solution. I actually use sodium iodide in my demo or in my example, but it works the same way, so it doesn't matter. Notice that as drops are added, what's forming in the middle. So it's a yellow solid. Those are precipitates. Remember how we talked about precipitates forming? Those are solids that come out of solution at the end. You started with these clear solutions. Now you're forming this bright yellow precipitate. And that is lead iodide, lead 2 iodide. And we're just going to do the same thing over and over again, I think. Oh, I think they're just trying to show a little bit more of the solid. All right, I'm going to go ahead and move past that. Maybe. All right, so the last thing that you all are going to write down is going to be your combustion of a hydrocarbon. Go ahead and copy in the missing information, and then we will discuss. So I don't have a demo for this one because we actually have a separate day that we'll do all combustion demonstrations. But the one thing that I want you to make sure that you're aware of is that in a combustion of a hydrocarbon, and a hydrocarbon is going to be this compound that has carbons and hydrogens in it, that you will always have the same generic equation. The hydrocarbon reacting with oxygen to give you the same two products every single time, which is carbon dioxide and water. That will always be true. It doesn't matter. I gave you an X and a Y because they could be anything. It could be C2H6. It could be C3H8. It could be any hydrocarbon. If it reacts with oxygen in a combustion, you will always get CO2 and H2O. So you already know what the products will be. But you also have to make sure that oxygen is a reactant, because if oxygen is not a reactant, there will be no combustion. If all you had is a hydrocarbon and then an arrow, that's going to be a decomposition reaction, because you have to have oxygen for combustion to take place. So keep that in mind. You need fuel, which is your hydrocarbon, oxygen, and you get CO2 and H2O. All right, now I'm going to move my head out of the way. I have linked this into the calendar. So if you can't see what's on my screen, you can go ahead and pull up that page, or you can print it out. So it's a picture. So if you can print it and you can answer all the questions from there, you can do that now. Otherwise, please copy down these 10 equations. And I want you to take some time to try to determine if they are synthesis, decomposition, single displacement, it's the same as single replacement, double replacement or displacement, and or combustion. So take a minute, copy those down, answer those questions, and then we'll go over them. All right, so very quickly, let's do this together. So since I started with an element and a compound and ended with a new compound and a new element, remember H2 is the elemental form of hydrogen, I know that this should have been, I'm going to snip this, actually, I'll just write with that. This should have been a single displacement or replacement reaction because I have a single element, and a compound, and then I have a compound and an element. And if you look back at your notes, the one that will do that is a single replacement reaction or single displacement. All right, the next one is starting with CO and O2 and getting CO2. Now, this looks a little bit like a combustion reaction, but it's not because there's no hydrocarbon and there's no H2O. So since I started with two reactants and ended with one product, you should have said synthesis. All right, the next one, I have a compound, another compound. And what happened is these two things traded places, and I have a new compound and a new compound, which means this should have been a double replacement or double displacement reaction. This one starts with one single compound and breaks down into two. So if I start with one, it's going to be a decomposition every time. The next one has a hydrocarbon and oxygen to produce CO2 and H2O. So this one is a little misleading for a lot of people. They have a hard time with this one. But because it's that same generic formula that we had at the very end, this would be a combustion reaction. Number 6 is an element and a compound, a new element and a new compound. So this looks a lot like number 1. And the reason is because anytime I have an element and a compound on both sides, I know it's going to be a single displacement or single replacement reaction. Ki is a compound, it's potassium iodide, but Cl2 is the elemental form of chlorine. So you end up with a compound and an element, and then you have a new compound and a new element on the other side. Even though it's I2 and Cl2, that is the elemental form of those elements because they are in Brinkelhoff. And so this is going to be a single displacement reaction as well. This one has two elements on the left and one single compound on the right. And anytime you have one substance as a product, you know it's going to be a synthesis reaction. The next one starts with one single reactant and breaks into more than that on the product side. And anytime that is true, it's a decomposition. And last but not least, we have a hydrocarbon reacting with oxygen to produce CO2 and H2O. So that generic formula tells me it's a combustion. All right, guys, I hope you guys have a great day, and go ahead and fill out your participation log for the week and submit that to me before 3 o'clock today, and I will see you all soon.